So let's get started. So today we'll finish the last part of the storage device, the flash transmission layer, and then we will move on to the IO stack slides, like lecture 2. So you can download lecture 2 on E3. Okay. So before moving on, we'll also do the same thing to quick recall. So last time we talked about there are errors or like there are retention errors in SSD. So the definition of retention error is cell cannot permanently retain electrons. So we also show you actually, no matter in what kind of PE cycles, there are probabilities to happen retention errors. So just about how serious it is. And then we also do some analysis. We can see the retention error usually the highest two probability would be from stat 00 transits to 01 or from 01 transits to 10. So the reason is because retention error, which usually means the electrons will flee off from the floating gap. So actually the electrons will become fewer, and it shows like for stat L3 to stat L2, it means the electrons will be flee off. So there will be fewer electrons in L2. So 00 to 01, which means decrease the decreased amount of electrons. Also the same from 01 to 10. They are both meaning it is about to decreasing the electrons inside the floating gap. Okay. So this is what happens actually when there are electrons moving across the dielectric layer. Then the dielectric layer will become thinner and thinner. So one day the dielectric layer will lose the capability to retain the electron inside the floating gap. Okay. And we also talk about actually there's two ways to know how serious the error is. One is using the PE cycles, the other is using a bit error rate. And we will talk more about the bit error rate part today. Okay, so this is actually showing from single level cell to quadruple level cell, like they're changing on a PE cycle. So actually the phenomenon will be when there are more, when one floating gap needs to demonstrate more levels, which means it is going to represent like from 1 bit to 4 bits, then their PE cycles will also get decreased because it is harder to differentiate like higher bit cells. Okay, for SLC it is easier. No matter how serious the error is, you just need to determine it as from the like a lot of electrons, or there are very few electrons. So it is quite simple. But when it comes to like QLC, which means you need to differentiate across 16 stages. So because 16 stages, actually there's very few errors, then it is very likely the two very close stages, they will overlap with each other. Example would be look like this slide. This is using like multiple level cell. We only use 2 bits. Okay, so when we are talking in this 2-bit scenario, you can see there's 4 possibility, right? So you can think about this step, which means there are full of electrons inside the floating gap, and 1 means there's very few, or even there's no electrons in the floating gap. So retention error means like your distribution will become looser because some of the cells may not be able to retain the electrons inside the floating gap. So the distribution will move to the little bit left-hand side, so it becomes looser. It is not this tight form. Okay, and then what means error? Error means like if you use this reference value, voltage value to do the differentiate, and then if you cannot clearly differentiate to cut it into 2 different stages, then there might be possibility to have error occurs. So when there is a possibility that you will pass the error, actually what it is going to do is to slightly change the reference value, because as we say, this voltage reference is going to clearly split out the left-hand side or right-hand side distribution. So now the dotted blue line now cannot do this things correctly, right? Because there's part of it, like if you cut here, then part of the zero stage will be mislabeled as 0, 1 stage. There is some probability like this. So what we are going to do is just to move the reference value from the left-hand side, and then to move it again to the left-hand side. So when we found like actually this dotted line will be a good reference value between 0, and 1 because it is easier to cut the stats into the left-hand side and right-hand side, and there is no overlap. So how to know we can stop? It depends on the bit error rate, because if now let's using this voltage value, we can get a super low bit error rate, which means it is a good cut. Okay, and this methodology is called retry, because in this example we retried 2 times, right? And in the real case, according to some papers, like it is possible to retry like 21 times or 16 times. So it just depends on the status of the patch at that situation, at different situations. Okay, so this is just going to show you retry actually you sacrifice the performance to get a better reliability. So the more serious retention is, then the more retries the SSD controller needs to try to achieve an appropriate one. Okay. So this is all about like retention and how to deal with the retention. And after retention, we talk about a more like software part, like SSD architecture. So SSD actually there are some limitations, and one of the notorious one is the sequential write constraint, because the block size is larger than the patch size. But when we are going to do the erase, we can only apply on a block linearity, on a block linearity. So actually, you cannot do the in-place update directly. You cannot just erase a patch. You can only erase a block. Therefore, flash translation there needs to hold the sequential write constraint. According to this constraint, actually we can only write the patch that is clean. We cannot write a patch. This is like there's already data inside. Okay, but how to achieve this kind of stuff? Actually, address remapping is quite a simple way to achieve it. Okay, so this is just a like very simple example for address remapping. So given like you have a NAND flash patch, we say logical block address is 500, and given a physical block address. So physical block address is the static address for the NAND flash. Okay, so every physical block address, it is static. It will not be changed. For this position, starting from which kind of addressing, then you will get a specific physical block address. So when we are going to update this LBA 500, this patch, what we are going to do is not directly update the data and replace TBA 800, because it is not legal to do this operation. A legal operation will be sequential write. So what we are going to do is to read out this LBA 500, or you can think about to read out the data, stay on TBA 800, and then we'll do the modification and then write it back to the SSD, but to a new patch. Okay, so this is called address remapping. Like LBA 500 will be renamed to a new PBA. So assuming this PBA is 1201, then we can update the mapping. After that, we will mark the prior LBA 500, the previous one, as an invalid patch. So for 1 day, if there are too many invalid patches in the block, then we will trigger the garbage collection to do the erase. Okay. So actually, what we are going to talk about more today is how to do the garbage collection. Okay. So we will skip this part. Okay. But actually, before talking about garbage collection, I have still some things to remind is the address translator. Because last time I think I'll go a little bit faster at this part. So I will go through this part again. Okay. So actually in the flash memory, there's blocks, right? And in each blocks, there are pages. So if we assume there are 128 pages per block, and then you can see each page, usually the page size is 4 kilobyte, but it depends. Different SSD, they can have their own spec. So they can have like 8 kilobyte or 16 kilobyte. Okay. So not only 4 kilobyte, there is still a spare area. So this is called a 64-byte overcommitted area. Okay, so you can see there's spare area, and usually this is for housekeeping information. So like, what is the relationship between the physical block address and the virtual block address? This kind of information will be maintained in the spare area. Okay, so let's skip this part to the real instance. So there are two very famous address in address translation mode. One is called patch label, the other will be the block label. So patch label is going to translate the address in the patch granularity. So this is the address translation table. So we have the format, like this is PPA, and for PPA we are going to indicate the block and the patch. Okay. And given there's a logical block address, so let's start from index 0, 1, 2, 3, 4. This is the logical part. And the physical part, I mean, it will be mapped to, for example, for this one is physical block 0 and the third patch like this. Okay, so when we are going to read the data from LBA3, and when I say we are going to read is when we are users, then our perspective is an application. We are going to send a request to read out some data from the SSD. Then probably we are using the logical block address. So physical block address, it only be maintained, only the SSD controller can know which is the physical block address, where is the block address means. Even for the operating system, even for your CPU, they all don't know. Okay. Okay, so this is the layout. This is block 0, and this is patch 2. Okay, so when we are going to read out the data, like this is like data will be stored in the purple area, the data area. And in the spare area, usually like it will maintain the information, for example, like LBA3. So this is for housekeeping. If we can validate, oh, your request is like from LBA3, so we can make sure our address remapping is correct by checking the spare area. Okay. So if our next comment is to write to the LBA3, for example, we are going to modify the data in the LBA3. So the thing is, we cannot do the in-place update. We cannot just do some update in block at the position of block 0 and patch 2. What we are going to do is we are going to read out block 0 and patch 2 and do the modification inside of main memory. So after doing the modification, we will once again write back to the NAND flash to a new position. So this is a new location. This location will be like block 1 and patch 255. And we will write our new data inside this. So we will update our patch table. We will update our address translation table. So this translation table, the PBA part will be updated to. Okay, but we're still not finished. We just finished maintaining the translation table. Okay, so we are going to mark block 0 and patch 2 as invalid. So in this case, this patch will become an invalid patch. So invalid patch, which just means we just use a bit to mark it as invalid. We're not really do the deletion, or we're not directly erase it. We just mark it. So we don't really pay for the extra performance overhead. So until one day, there's no sufficient room for the SSD to store data, then the garbage collector will come back to check, oh, actually this blocks, there are a lot of embedded pages. So let me garbage collect this block. Until that time, they will have issue a real erase comment. Okay. Okay, so last week we will do a very mathematical stuff. We calculate how much of the overhead will we spend when we are going to maintain this patch table. So the thing is, actually patch table is quite intuitive, right? But the thing is, it will spend a lot of overhead to maintain the table. So roughly speaking, if you have a SSD, then you need to spend like 1/1000 of the SSD size for the maintaining the DRAM. So this DRAM can maintain the address registration table. So if you don't want to spend so much of the overhead to maintain the table, what we can do is block label address translation. So block label address translation, it is quite different. So the physical block is like this. And the key thing is there is no more patch information because we can only do the block label maintenance. So this is the index from BBA1 to like N. And if we are going to write LBA28, what we are going to do is, because we don't have patch information, so we are going to do the calculation to calculate where is the patch. Like we will divide by 6. And the 6 is, if we assume there are 6 patches in one block, then we need to divide by 6. So after this divisions, we can get 4, right? So 4 means the VBA number is 4. Okay. So after getting the VBA 4, we will read out like, hey, actually, the real data will be stored on block 24. Okay, but we need to know which patch it is. So we use the modulation to calculate where is the patch. So after the modulation with the patch number like 6, we can get, oh, actually the data is stored on patch 4. So it's like this. This is patch 1, 0, 1, 2, 3, 4. Okay, like this. But because when we are going to write the data to this patch, what we are going to do is we need to allocate a full free block. Okay, because we are using a block label. So actually we cannot find any patch. We can move it directly. We should find a whole block, and all the patches inside the block, they are all free. So at this point, we will write our new data to the same patch, the patch 4, in a new block. We say block 62. So block 62 will then be updated back to the address translation table. Sorry, here. So here 24 will become 62. At the same time, actually, we will move the those valid data in the prior block to a new block because we only have a block label information. So for block 24, for the rest of them, we are no place to update their information. So we need to move their data. We need to copy out their data to a new block. In this case, we don't really need to change the information in the address translation table. For those kind of mapping to like VBA 4, for VBA 4, they can all be mapped to like block 62. Okay. So, because after doing the copy, all the data in the block 24 will become invalid. So in this case, we don't really need to do a copy collection. We can just erase block 24. Then block 24 becomes a new block. Okay. So as we do not maintain the patch information, so the overhead for the memory is quite low. So look at the DRAM consumption now. FTL, the patch table FTL, it consumes like 2 GB, assuming you are using a 1 terabyte SSD. And your block label, actually, you only need 11 megabyte. Maybe you will think like, hey, why RAM consumption is that important? I mean, your computer usually has more than like 8 GB, right? But this RAM consumption is not the DRAM you equip it in your PC or notebook. this RAM consumption is the DRAM inside the SSD. So you can think about like the small SSD inside, you need to equip with a 2 GB DRAM. So the more DRAM you have, the more expensive the SSD will be. Okay, so this is why the reason. So if you are using a block label, you only need 11 megabyte, then you even don't need DRAM. You only need a very small like SRAM cache. It is also possible. Okay, so for some device, if you don't want to pay too much of the energy consumption and you don't want to have that huge DRAM, you need to choose a block label solution. So usually block label solution you can use on those kind of embedded SSD or like edge device. And for FTL, the sacrifice will be the RAM. But the good thing is we can make sure the write time is super low compared with the block label. Because the block label, we need to move all the valid pages from one block to another block. So write time will be super high. Okay, so this is the difference between the FTL and block label. And then in the industry, it depends on what kind of use case. So if you are talking about an enterprise SSD and people were using the patch label, but if you're talking about an edge device, people don't care that much of the performance, but people care more about the price and energy consumption. Then block label can be one possible way. Okay, so after talking about the edge translation, we are going to talk about the garbage collection. So when we choose to use the patch label, then probably we need to do the garbage collection. So a simple method, a simple flow for the garbage collection is to pick a victim block, and then we do the live patches copy. So we copy all valid patches from the victim block to other new blocks. So like this. We will copy out the valid patches from the victim block to a new free block, and then all the patches inside the victim blocks can become invalid. So at this time, at this moment, we can trigger the erase command to erase the victim block. Okay. So after doing the erase command, after issuing the erase command, the victim block will be released and it can be used next time because it becomes all full. Okay, all free, sorry, not all free. Okay, even this looks quite simple, but actually there's a lot of things need to discuss for this policy. So the first is how to decide which block should be reclaimed. So come to think about, like, if each block, usually the block size is like 1 to 10 megabyte. So when you are using a like gigabyte or terabyte label SSD, like the space, so the number of blocks will be very close to medium blocks. So when you are going to decide which block should be doing a GC in a medium scale, then which one would be a possible candidate for doing the garbage collection? And the second one is, where is the destination? So is it like any free blocks, is it possible? Or actually we need to do something more fancy. We need to differentiate the property of each pages and we put the different destination. So if you already read some papers from SSD, you will frequently heard about a thing called hardcode separation, which means it is not only to put the valid pages to one block. We should separate them into different blocks. Okay, so there are at least two different ways we can think about this garbage collection. So let me first show you a very simple one, the greedy one, and this is more intuitive. So greedy one is to clean the block with the most invalid patches. So for the greedy solution, we only talk about which victim block should we select. We don't care about the destination. Any destination is possible. We only care about which block should be reclaimed, which block should be doing the GC. So this is also very simple because the good thing for greedy is it minimizes the live patch copy overhead. Because the most invalid patches, which means the least number of valid patch, right? Because the overall number of patches in the block is the same. Usually it's 128 or like 512, depends on the different SSD. So the most invalid patches means the least valid patches. So we can minimize the live patch copy overhead. And live patch copy overhead, usually it is identified as the most expensive operations for doing a GC because there are a lot of data movement will be triggered. But the bad thing is, like, if there are different access frequency on different data, which means some data is cold, some data is hot, then when most of the SSD space is filled with static cold data, so a few number of blocks might be repetitively selected, erased, and worn out quickly. So when people talking about garbage collection, I mean, performance is one factor. There is another factor as lifetime. What I mean lifetime is the lifetime for each block. Because we know if we frequently erase and program the same block, the blocks one day will be worn out. Okay. So to avoid this kind of stuff, people usually talk about, hey, then we need to do something like wear leveling. We need to evenly distribute our write or erase to all the blocks, not only focus on a few group of blocks. Okay, so after greedy, people are talking about then, because we know there is hot and cold, so why not just doing some like cost benefit stuff? So what is cost benefit? We clean the block with the largest benefit cost value. So the cost benefit, usually we'll use a formula. So this is the most simple one. So benefit over cost. And the calculation for benefit is the edge times 1 minus V over 2V. 2V is cost. So what does it mean? So you can think about like this, because we are going to clean the block with the largest benefit cost value. So for each block, we will maintain this value. And the edge means the invalidated time period. So how cold the block is. And the mathematic is T current minus T last patch invalidates. So for this number, if it is larger, which means it is colder, and which means at a very long time, the block, I mean, any patch in the block doesn't be accessed for a relatively long time. Be invalidated. So this is the edge. And V means percentage of valid patches of the block. Okay. So 1 minus V, which means the percentage of invalid patches of the block. So what we are going to clean is the largest list value. So which means when a block getting colder will be higher probability, or there are more patches that are invalid. So 1 minus V is the same consideration for the greedy. Greedy is also talking about we are going to choose the block with the most invalid patches, right? So in the cost benefit, it consider an extra perspective, the edge. And 1 minus V is the same as the greedy. And what about 2V? Why 2V is using here? Because 2V means when we are doing a live patch copy, it costs 1 point to read out and another 1 point to read out to other blocks. So total, we're removing 2V. Okay, twice the percentage of valid patches. We need to read it and then we need to write to other place. So this is a way to just to formulate, like to push the greedy to consider the code, hard and code. But it is still not enough because cost benefit and greedy, we only talk about which block should be selected, but we do not talk about where is the destination. The destination before the whole hard code separation is any free blocks it is possible. Okay. So the thing is, if we mix the hard and cold patches together, which means in this block, it is possible, like for some patches, they will quickly become invalid because probably they are hard patch. Hard patch means they are going to be updated very frequent. And there are also cold patch. So cold patch means their access is very infrequent. So which mean they are cold. Okay. And if we mix both of the patches together, like it is likewise, we need to do the garbage collection very frequent. Because if we think about like this, if we can separate, like if we can gather all the hot patches in one block and go and gather all the cold patches in another block, then actually the block containing all cold patches, they do not really need to do the garbage collection because they are always valid patches. And for the block containing hot patches, we also don't really need garbage collection super frequent because they are very frequent. Sorry, they will be very possible become the blocks with all invalid patches because hot patch will becomes invalid very soon, right? In this case, we can minimize the live patch copy overhead. Okay, but the idea is quite simple, but there is some technical problem here. So how to know the hard code degree of each patch? I mean, we just roughly say hot data is the data that getting a lot of access, and cold data is roughly we say the data is very like static, nothing update will be happen in this patch. But how to define the degree? So there are several ways. The first one will be counter-based, and this is more intuitive, which means for each patch, we maintain a counter. So when a patch is getting access, getting update, we'll increase the counter. Okay, but counter-based has several issues here. The first one is the size of the counter. Because you can image if like for each patch, for each 4 kilobyte patch, you need a counter. Then if you are using a 4 gigabyte, just 4 gigabyte SSD, it is super small, but you need to maintain a million counter. So 1 million counter, then you need to prepare that much of counter, and each counter in what size. So if you are saying, hey, I'm going to minimize the overall overhead, then you say, I just need like 8 bits per counter. 8 bits means you can only represent 2 to the 8. So 2 to the 8, 2 to the 8 is 256. So the counter only increased to 256 and you will stop there. Okay, so if you are going to make it more precise, if you are going to use this device for a super long time, probably 8 bits is not enough, but how large it is will be a good point. Okay, so before answer this, there is also another question is, so when to reset a counter? Because come to think about, if you are going to use this like NAND flash SSD for like couple of years, then probably for some patches you will be accessed like hundreds or thousands of times. So even a super large counter might not be enough. And then even you give a one patch a super large counter, sorry, a super large size of counter. How about the other? So another way to think about is, so maybe there is a way to reset a counter. So even we just give it like add bits counter. So if we can find a good point to reset a counter, then we can reuse the small size counter, but we can still accurately know like how much of the access it is. So actually those 1 and 2, there are open questions. So when you are designing the solution for SSD, people are usually focused on like how large the counter is and when to do the reset for the counter. So this is just a quick example, like different patches, we maintain a counter. But you know, like when this patch is a hot patch, probably maybe one day you will get like 100 hits. Then like for 1 year, 365 days, you will get like 36,000 times of the access. So you will need a super large counter, right? So how many bits are enough is a quite important things. Okay. So if the number reaches the maximum, we need to do a reset. But how to do the reset? Because when it like just intuitive does the reset, then you'll go back to 0. Then how can the system know patch 3 is a super hard patch? Okay. So there is another way to think about this is using a list best. List best you guys also are very familiar with because it's just like the ARU or FIFO. So you can think about if one patch getting hit, you move into the LRU or FIFO queue. So actually, for the queue, which means all the hot patches, they are all inside the queue. Okay, but how to maintain this queue is a question, because given this list, like patch 5621734, okay. So now, if you access patch 4, according to, if we are using the LRU, according to LRU, patch 4 will be moved to the head, right? And usually we will say in the LRU, like for the head, it is hot, and for the tail, it is cold, because head means the least recently accessed patch they're there. But least recently accessed doesn't equal to super hot, right? Because it is possible, what if this is the first time to access patch 4? Then maybe patch 4 is super cold, but it's just very lucky, like it's just getting access now. So when we do the like maintenance, when we are doing the GC, we just see actually patch 4 is super hot. Then it doesn't really so accurate to reflect how hot each patch is. So this is the problem for this batch. Okay. Okay. So as we mentioned before, like not only performance, because another very important thing for SSD is lifetime. I would say usually for the SSD vendor, usually lifetime or like the error correcting or like error handling is more important than performance, because performance is a thing just like you user just can wait for like 1 second or 2 seconds, so you will just get annoyed when you are waiting there. But error, which means you will get the wrong data, and then this wrong data, even for the user, maybe you don't know the data is wrong because you read our data, there's already error. So the answer, the return data, there's already error data in there. Okay. So for this point, performance is a things like users can aware of. So they can predict, oh, there is a performance drop, so you can just wait for like 1 or 2 seconds. But if there is an error, then which means your data will be corrupted. You can no longer read out the correct data. So for the vendor part, actually they put more efforts on how to like extend the lifetime for the SSD and how to deal with the error. Okay. So there is one very, I would say like smart way to extend the lifetime of SSD. I mean, it is also possible, like you can depend only on a super strong ECC. The ECC is error correcting code. So you can depend on this kind of very strong mathematical, and um, if you are affordable for very pricey SSD, then you can get a super strong SSD. Okay, but there is some way to solve this. Oh, sorry, not solve. There is some way to alleviate this kind of reliability issue is doing this wheel leveling stuff. So wheel leveling stuff, actually the goal is to level rise to all SSD patches. Because we all know for the SSD, it causes the errors when the dielectric layer becomes so thin, right? And the dielectric layer is because you move the electrons between them, between the P substrate and the floating gap. So a key idea is let's just distribute all the write to all the patches. We not only focus on few patches, because if you have like million of assets, if this million of assets only apply on 2 patches, then probably the 2 patches will become wear out very soon. But if you have million assets and you have million patches there, if you do the wheel leveling, so after million assets, each patch actually only get 1 asset, then it is still super healthy. So wheel leveling, as its name, we are going to evenly distribute our writes to all the SSD patches. Okay, so just like this. So if we just forget the wheel leveling, then probably you will see things like links. Patch 4, it gets super frequent access. So patch 4 and patch 6, they'll be worn out in a very early stage. But you see like patch 2 is still very healthy because there is no access to patch 2. But considering the whole device, if there are a percentage of the pages they're getting worn out, the whole SSD cannot be used. The whole SSD should be replaced. So even there are some pages like page 2, they'll never be accessed, then this SSD should be still replaced. So a better way is to lag less. To after the real leveling, all the pages they get a very near number of the access. Okay, so in this case, the whole SSD can endure more writes compared with the case with no real leveling. And this decision, sorry, I would say like this solution, actually, you usually don't really need to depend on extra hardware device. Because like ECC, usually we need hardware accelerator. Okay, you need very strong, powerful controller to calculate the ECC. But real labeling, usually it's just about the decision where to put your data. So it can be directly integrated with the garbage collection. Okay, so there are two ways for real leveling. One is called dynamic real leveling. So the other is called static. Dynamic real leveling is to level writes to free blocks. So during the writes, we will choose about where to do the leveling. Okay, so actually we only choose free blocks with a lower erase count, and we will redirect the write to there. Okay, so this is called dynamic. And I would say actually dynamic real leveling doesn't perform well compared with the static real leveling. Even static real leveling sounds like not a very smart solution, but static real leveling is powerful a lot than dynamic real leveling. Because for static real leveling, which means it will level writes to all the blocks. So no matter it is used or unused, we can level the writes to all the blocks. Okay, so the way to achieve the static real leveling is to moving code data to blocks with higher erase count. Okay, so static real labeling, you can think about it is even the block where there's no write to this block, we still can proactively move the data in that block. So for static real labeling, we can achieve an even better real labeling results. But the cost is you need to spend extra moving overhead, because for this use block, even there is no write to this block, we will still move the data from one block to another block just for achieving a better real leveling result. Okay, so you can think about static real leveling to track the performance for getting better reliability. Okay, so here is more kind of details for dynamic real leveling. So as you know, there are two different kind of data, hard and cold data. So we define hard blocks means the blocks mainly containing hard data, and cold blocks means block mainly containing cold data. So running dynamic real leveling, it can only level writes to hard blocks. What is the reason? Because for those cold blocks, usually there is no write to them, because the data inside the blocks, they are cold. Cold data means there is no update usually will be performed on those blocks. So if there is no write to those blocks, we will not really do the real leveling on it. This is based on the definition for dynamic real leveling. So which means if there are a lot of cold data in the systems, those blocks will be always cold blocks. And then only the hot blocks will do the real leveling. So the hot blocks will accumulate the PE cycles super fast. And then you will reach the maximum PE cycles, and you will get those hot blocks will start to show the arrow. Okay. Static real leveling, on the other hand, it can level writes to any block which is almost worn out. So it proactively moves code data to hot blocks. So this is the ideal, result after running the static real leveling. What we are going to do is to let all the blocks to endure even close to maximum PE cycles. And for this one, actually, what we are going to do is proactively move the data in a code block. Even there is no write to the code block, we still can trigger it by the flash controller. We trigger it proactively. We just move it to some hot blocks. Okay. So challenge is just as I mentioned, trade-off between performance and lifetime. Okay, so I think there are 3 examples for showing you how real leveling works like. So first of all, it's called a dual pool real leveling. This is very famous solutions. So dual pool wheel leveling, actually it is about to migrating code data from young blocks to old blocks. Okay. So code blocks updated less frequent and old blocks, which means higher PE cycles. Okay, because higher PE cycles means these blocks are very close to be worn out. So if we can move the code data to these old blocks, which means the PE cycles will stop increasing for those old blocks. Okay, so given the example here, actually there are two pools, and the bottom pool is for the code data, and the upper pool is for the hard data. And this block is the oldest block. Oldest block means it gets the super highest P cycles, which means this is very close to be worn out. And this is the youngest one. So youngest one means it is the very, like there is no frequent access. There's no access in this youngest block. So for this adaptive pool resizing, it can prevent some blocks never be selected because all the blocks are here. So actually all the blocks will be selected. And it doesn't really need so much of maintenance overhead because we do not care exact edge. I mean, we just do the comparison between two blocks, which one is older, which one is younger. And if there is a code data count, for the code data, we will put to the oldest block to cool down the oldest block. And for the hard data, we'll move to the youngest block to increase the PE cycle to let the youngest block absorb the access. Okay, but still, there's still some problem. I mean, how to maintain the access count for the hard code data? Because in this situation, what we can save is the maintenance overhead for the block. But for the data itself, there's still problem for like what is the access count for the data. Okay. So let me show you another perspective for the wheel leveling. It's called progressive wheel leveling. Okay. So in the prior solution, we show you a very typical wheel leveling solution for static wheel leveling. And for the progressive wheel leveling, it is going to ask one question. When and how often static wheel leveling should be performed? Why there is this kind of issue? Because if you recall to this solution, which means if there are two blocks, and these two blocks, they have slightly different access P cycles difference, then we will judge the one with higher P cycle is old, and the one with fewer P cycles young, right? It's just about the comparative. But the thing is, maybe they are all in a very low ratio. For example, if we say if the oldest block now is like 100 PE cycles and the youngest is maybe 1. Okay, even if it's 100 and it is 1, we will still trigger this solution. Okay, but the thing is, maybe the endurance of the PE cycles, each block can endure up to like maybe thousands or even 3,000 or even 4,000 more. So actually, we don't really need to trigger the wheel leveling so early. And this is what an ideal case. So in most of the static wheel leveling, before progressive wheel leveling is proposed, actually the wheel leveling counts, which means they proactively trigger those kind of extra live data copy actually is super high. But for those kind of wheel leveling counts in the amount of written data is still in a few, which means there is still not too much of data in the SSD. Actually, we don't really need to trigger wheel leveling this frequent. Okay, so what this progressive wheel leveling is going to tell us is if this SSD doesn't contain that much of data, we can trigger the wheel leveling super lazy, which means the SSD is still in the early stage. So for early stage, we should try for a better performance. Let's run the software with static wheel leveling. Okay. So if one day the SSD now contains like more than half or even more than like 75% of the data inside, which means it gradually moves to a last stage, then we can aggressively run the static wheel leveling. So before this paper, actually most of the research, they are assuming we are going to trigger wheel leveling anytime. But this paper says in the very early stage, like the dark blue bar, expected wheel leveling count, we don't really trigger that much of wheel leveling. We trigger when there is a lot of data in the SSD. Okay, so this is another perspective for the triggering SSD part. Okay. Oh, I think it's time. So I think let's take a 10 and come back later.
请问作业可以用 WS 东西，就它会因为虚拟的关系造成数据的问题。
再次，就是
它可以用 WS 的东西吗？
哦，这个你跟助教确认好了，因为作业做了改的，对，你就写进问题，问一下他们，这样
问一下这个。
对。
All right. So let's come back. I think there are a couple of interesting questions in the chat box. So the one is, if an SSD already used garbage collection, why is well leveling still needed? So you can think about like this. Garbage collection is conceptual. It's a conceptual like design. Like we are going to do to reclaim some blocks to some place, right? And usually well leveling, they can be integrated together with garbage collection. So purely if there's only garbage collection, usually people don't really integrate well leveling if we don't really care the reliability. Because for garbage collection, like you can think about it just about to spare out like enough extra room for the space. So in a very original design for garbage collection, it doesn't care that much of reliability. But now, like people know, especially for now SSD, there's getting to QLC or even more level bits inside the cell. So they consider more about the well leveling. Then they can integrate the garbage collection with the well leveling together, so they can be designed together. Okay. And usually garbage collections, it runs, usually people will say it's in the background. So if now your SSD is now in a very, enduring a very intensive workload as very frequently, garbage collection will not be triggered because garbage collection usually need a good amount of bandwidth because you need to move live patches from one block to another block. Okay. So, and another thing is, so when to trigger the garbage collections or like wheel leveling, actually, there's over subscription area in the SSD. So even you have like 1 TB of the SSD, will contain a little bit more than the size of the SSD it just provide you. So when, for example, maybe it has like 1.1 TB. So there is always some extra like patches or extra blocks for doing this kind of garbage collection stuff. Okay, so this is called a like over subscription area. Okay, so let's move on to our last design for wheel leveling, because we talk about wheel leveling, like static wheel leveling is getting better reliability compared with the dynamic wheel leveling. And where should we do the wheel leveling? So progressive wheel leveling tells us we don't really need to do the wheel leveling super aggressive in the very early stage. And the last thing is, until now, we make the decision according to the PE cycles, right? Just like we know the block is in the high PE cycles, then which means it is an old block. The block with a super low PE cycle, then this is a young block. But are PE cycles accurate enough? So PE cycle is a very like roughly indicator for showing you for showing the SSD if the patch is healthy or not. So PE cycles cannot accurately reflect device reliability. And the reason is because the cell variations or process variation, which means if we have 10 of millions or 100 of millions of the NAND flash cells in the SSD, so different cell that has a different thickness of the dielectric layer. So this is by nature, right? So in the same, even in the same patch, they might have different bit error rates because different cells, I mean, in one patch, there is like thousands of NAND flash cells. So different cells, they can have different bit error rate according to their thickness of the dielectric layer. So this is very possible to happen in one patch. There are some cells that are getting error easier than other cells. Okay, so I'm just using one very toy example to let you know what is the design concept behind this called error rate aware wheel leveling. So the concept is block with more healthier cells, which means lower error base can endure more writes. So given there is an example, like we are going to play a game, and there is four members in the team. So there are different characters, so they have different property. And the rule is there's only one rule. So if there is one character, if the one character is died, then it is game over. So different character, they have their different capability, which means, for example, wizard, they have a very less HP, but maybe it has a more powerful other like magic power, something like that. And then you have a tank. Your tank has a super high HP compared with the other character. So conventional wear leveling, you can think about each character is just like a cell, because different cell they have different variations, right? So some cells, they just act like a tank. They have a super thick dielectric layer, so they can endure a lot of writes. But for some cell, it's not healthy. It's unhealthy. So it's just like a wizard, like they have a fewer HP. And this is how conventional wheel leveling looks like. Because like wheel leveling, we're going to evenly distribute all the write to all the cells. So it will be like less. So the patch will be corrupted, will be marked as invalid once the bit error rate reaches some point. And the bit error rate means those wizard HP, they're finished their HP, right? Which means those unhealthy cells, they're already worn out. Okay, and this error rate aware solution is like less. We don't really look too much into the PE cycles. We care more about the situation for each cell, because bit error rate, actually it can reflect how much of errors there are in each patch. So for those patches that have more errors than others, they should be as an unhealthy patch. So they can endure more writes. Okay, so we need to identify which patches that have more healthier cells inside. Okay, in this case, we can earn way more of the lifetime for the SSD. Okay, so this is just a idea to let you know P cycles is not the only indicator. There is still others, just like bit error rate. And bit error rate, if you still remember, it depends on the ECC. So each time when the SSD controller read out the patch, SSD controller will run the ECC to check how much error it is. If there are too many errors, your SSD controller will run the retry. So if the error is acceptable, then the error will be maintained. So it can be used for doing the wheel leveling. So this is just a brief idea behind this solution. And actually, this is the last slide for the storage device part. So questions? Okay, so if you have questions, you can put on chat box. And if I have time, I can pick some interesting part to answer. And let me quickly switch the slides to another one, our lecture 2, one moment. Okay, so lecture 2 is IO stacks. So it is all about the software part. So software part including like operating system more. Okay, so because software part is more about operating system, so I will first give you a quick recap of what you should know, those prerequisites for the operating systems. So if you already took the operating system last semester, I think you'll be super familiar with it because there is just a condense for all the things you learned on the last semester. Okay, so there are 3 things you need to know before moving more about the IO stacks. One is about how CPU access memory storage device. So the second one is how Linux kernel works, because operating systems in this course we will target on Linux kernel. And then what is interrupts? Okay. So this is a computer organization. I think in the first class we already talked about. So there are 3 main devices in the computer organization. Computing device, which means CPU, GPU, memory device, which means DRAM, and IO device, which means hard disk drive and SSD. So your data, according to the von Neumann architecture, you should always move from the memory to the computing unit. Okay. So if the data is not in the memory, probably it will be in the IO. So we will move from the IO device to the memory. Okay. So CPU will fetch an instruction from the memory. So CPU, there is a special counter called program counter. So this counter is just thinking about, it is just a pointer to the next instruction. Okay. And this is what your code look like from the CPU perspective. So you write a code and then you do the compile to the assembly, and then finally you will become a machine code. So each line for the machine code, we call it instructions. So instruction will like the add instruction, or like you have to move the instruction, those kind of stuff, they are all instructions. So CPU will run the instructions one by one. So we call it fetch. So after CPU fetches, CPU will do the decode and execute. Okay, so this is all you learn in the computer organization course. And CPU fetch next data. So CPU, how to fetch next data? Actually, the program counter will automatically increment the program counter. Okay, because this each of the memory address, the width is the same. So the width is like 4 bytes in the 32-bit systems, or like 8 bytes in the 64-bit systems. Okay. And CPU only does routine work. So CPU will move from one instruction to another instruction one by one. Okay. And then I think we already talked about this. The challenge without operating system, I will just skip it. I think this one can be skipped. Okay. So how CPU access data in memory storage? Because this course we talk all about the data stuff, right? So there are memory device and there is storage device, and there are different kind of data. There are process data and there are file data. So process data, sorry, Okay, it's not working. Okay, so process data means those data that are in a heap and stack area. Those are process data. So when you are writing a program, you say you are going to use a memory allocation from C library. Those are belonging to the process data. Or when you have a function code, those are process data. And what about the file data? File data is those when you are trying to use the file read. They are called file data. Okay, so some portion of the file data, they will be in the main memory. For example, those data in the patch cache. Okay, so patch cache means you read the file once and then you cache the data, cache this file data in the memory. So next time you don't really need to read out the data from the storage device again. Okay, so this is how process data being accessed. Usually CPU will directly use the low sort instruction to get the data from the main memory. Okay, so this is like a process data. Okay, and there is another one is like file data. So for file data, we will use the system code. So when you are using the like fread or fwrite in the C library, the library will hook with the Linux kernel, for example. So you will call a read and write system code, and then the rewrite system code will dive into the patch cache file system and connect into the context switch. So the patch cache here list is in the main memory, and usually file system is for the storage device. Okay, so this is just going to show you actually different data CPU will use different way to access them. So even for file data, there is possibility some data will be in the DRAM and some data will be a file systems. Okay, and I think we need to come back to talk about one thing is what is Linux kernel or like what is an operating systems. So you can think about Linux kernel is just a process manager consists of a bunch of C and assembly code. So what do I mean for a bunch of C and assembly code? So you can think about, you learn from the operating system course, there is a like process scheduler, there is file system, and then there are memory manager. So each of the conceptual things in your operating system textbook, they will become a bunch of C and assembly code, and they will become a function, like scheduler function in the Linux kernel, or like memory manager function in the Linux kernel. So this is what I mean for a process manager consists of this, a bunch of C and assembly code. Okay. And there is a very typical question, is Linux kernel a process? And the answer would be, this is not a process. Okay. And this answer will depend on different scenario. I mean, if you are not using the Linux, you are now using the Microsoft, and or you using some other operating system, and this answer sometimes will become yes. So it depends on the design behind each operating system. But at least for Linux, this is not a true answer. Linux kernel is not a process. It's just a bunch of C and assembly code. Okay. And the details is actually it runs as a part of a user process. Okay. So actually for Linux kernel, they don't have their user part. They share their address space with the user process. Okay. So I think this explanation is quite long. So I just use a figure to let you know. So you can think about when you are going to write a C code, then for each programmer, you will get this area. So the bottom 3 GB, if you are using a 32-bit system, the bottom 3 GB is for user address space. When you are doing the memory allocation, when you are doing the function like creation, or you are going to new an object, so you will use this bottom 3 GB area. Okay, and then always the top 1 GB area, you cannot touch it because those are for the kernel. Okay, so your user program and process data is in this area. And for CPU, actually there is a spatial tag in the CPU. It's called the mode tag. So this tag is going to indicate the CPU now is in which mode. So if the CPU is in the user mode, which means the CPU can only access the user address space. Okay. So if here comes a patch fault, so what do I mean for patch fault? If now the CPU is going to get the data from the memory, but now the the TOB shows in the CPU say like, hey, actually the data is not in the main memory. It's not present in the main memory. So CPU know, oh, so then the data might be in the storage device probably. So the memory controller unit, the MMU, will trigger the patch fault. Okay. So for this patch fault, actually CPU receiving the patch fault will switch the mode from user to kernel. And MMU trigger patch fault and CPU change the mode. They are all hardware functions. So those are all running in the hardware. So CPU will do it automatically. Then CPU will switch to kernel mode. So until now, there is no software. They are all hardware in the Linux and Intel CPU. Okay. So this after CPU switch to kernel mode, the hardware procedure will keep going. So it will set up the register, and the CPU will know. CPU parent counter will be reset to the very beginning of the patch fault handler code. So like here, and then CPU will start doing the access. So CPU will fetch the first line from the patch fault handler and then to run the patch fault handler. Okay, so this is how CPU run the kernel. And this area, not only patch fault handler, there is also process scheduler. There's also file system, memory manager. They are all in this kernel address space area. Okay, so this is how CPU run the Linux kernel. Okay, so CPU switch to kernel mode to access the operating system code, including patch fault handler and blah, blah, those kind of stuff. But CPU does not need to switch the context. So just want to not to let you confuse with the context switch, because this is called mode switching. So CPU is still running on the user, like the same user context. This user doesn't be switched out. So this is not context switch. When we are talking about context switch, we are saying about we are going to switch from one user to another user. But now user is the same. We only switch to another spatial address space, which contained in the operating system code. Okay, so maybe this is still too hard to understand. So I have I think I'll have an easier one. So now if you think about a CPU, it's just like a submarine. So when CPU is running, it's batching the code, it's running the code, which means the submarine now is moving above the water surface. So this is about process A. So what do we mean like a CPU switch to kernel mode like this? The process A is still process A. The only difference is the submarine dives into the water. Okay, so this is the same CPU, the same submarine, and then it runs the same code because submarine doesn't change, it's still the same process. The only difference is the position is changed. So the kernel mode, the bit in the CPU, it changed from user mode to kernel mode. Okay, so this is just an analog to let you know how CPU access the Linux kernel stuff. And maybe you have some question about, but like there are still some very spatial kernel process they're working on the monitor system data that are called daemon. And that is true. For those process, they are slightly different from this Linux kernel definition, but because this is not a operating system course, so I will just skip this part. Okay. So let me give you a more detailed example. So this is the per process virtual address space. And if you're using a 32-bit systems, 32 bits which means you can addressing up to 4 GB of the space, right? 32 so 2 to the 32 is 4 GB. Okay. So if you are a programmer, as I just making an example, your code will be in this area. And then the operating system code will be in this kernel virtual space area. So this is kernel code, including the kernel data structure. So those patch table, kernel stacks, memory management structure, those kind of stuff will be in this area. And what are those in virtual address space? So those you learn, for example, the text section, data section, BSS section, which means the global variable sections, user stack, which are going to store your kernel, your user function, your heap when you are using the memory allocation from C library, and then those shared library. So STD library from C code, those standard library, they will be shared and they're in the memory mapping. So this layout will be the same across all the user process. No matter which user process you are writing, like they are using the same very similar form. The only difference is the data is not the same. I mean, for different process, you have your own text section, you have your own global section. Okay. And actually, they are all called the virtual address space. So what do I mean virtual? So have you ever thought about one question? So when you are writing a program, why you don't really need to care about like how many memory you are using? If you are running like 2 or even 3 process, like why different process will not use the same memory when there is no memory confliction? So this is because about the address remapping. So this is the physical address space. What I mean physical address space is the DRAM you really put it in your in your PC. So this is the physical address space. And then like this. There are 2 different user process, right? The right-hand side is the one called process 1. Left-hand side is called process 2. So process 1 and process 2, they are physically separated from each other. So even from a user perspective, you are seeing the same layout. This is all from the beginning, 0x, 000, and then to some place 0x. I mean, I think it's like FFF, something like that. So here, 3 GB, even from your user perspective, you are looking at the same layout. But from the hardware part, the operating system will help you to make up this joint region for different process. And then all the kernel virtual address, they will usually be mapped to the same physical address. So even this is 2 different process 1, process 2, but they are all mapped to the same Linux kernel. Okay, so here inside, like there are different patch tables and different user process, they have their own patch table in different like location in this area. Okay, so with using the patch table, we can achieve this kind of remapping stuff. Okay, so this is about, I think, a brief introduction for Linux kernel. Okay. So there is a following question. Then, how CPU work with hardware device? Okay. So when we are talking about hardware device, usually we are talking about the peripheral device. So peripheral device, there are including keyboard, mouse, and disk, hard disk drive, SSD. Those are peripheral devices. Okay. So there are 2 ways for CPU to work with this lower device. One is called polling, the other is called interrupt. Polling is about CPU periodically checks hardware status and responds accordingly. Okay. And interrupt is the device will send a signal to let a CPU know actually the device finished doing something. But how to realize interrupt? How device can interrupt the CPU? So this is a quite, formal definition. The hardware device will physically produce electronic signal and which are routed into input pin, blah, blah. Okay, so let me give you a quick example. So this is our motherboard. So on the motherboard, actually there are CPU chips, right? There's a very tiny CPU chips on the motherboard. And around CPU, usually there's 2 layers. One is called north bridge, another is called south bridge. So north bridge is going to connect with the very faster device, usually like DRAM. Okay, and sorry, north bridge and south bridge usually called a chipset. And north bridge connects to like DRAM and GPU, those faster device. So when you open up your PC, your motherboard, you will see your CPU. Surrounding your CPU, there are all DRAM. Okay, and there is salt bridge. Salt bridge is usually connect with like keyboard, hard disk drive, PCIe, SSD. Okay, so usually it is a little bit far from CPU. I mean, physically it is a little far from CPU. And here is interrupt controller. So interrupt usually, which we are meaning as those peripheral device, because they are slow. They are comparatively slow compared with CPU. CPU usually will have like 0.3 nanoseconds response time, right? But keyboard, hard disk drive, SSD, usually it is comes to like microsecond or even millisecond level. So they are so slow, CPU will not really want to wait for low slow device. So there are these kind of interrupt stuff. And interrupt controller is going to control the interrupts between CPU and the peripheral device. Okay, maybe you have one question, why there is no controller? Why there is no interrupt controller for DRAM? Okay, so the reason is DRAM will not interrupt CPU. So when CPU is getting the data from DRAM, CPU will wait here, wait for the response from DRAM. And the reason is DRAM is super fast compared with those peripheral devices. So the latency for DRAM is usually like 10 to 15 nanoseconds. So it is very close to CPU's response time. So this is the reason why there is no extra like interrupt controller between the DRAM and CPU. Okay, but there are still memory controller between CPU and DRAM. But the memory controller is not about to producing the interrupt. Memory controller is about to schedule the DRAM request. Okay, but yep, this is not the coverage for this course. Okay, and after 2019, actually all node bridge functions has been integrated into CPU. So node bridge, you can think about this as the memory controller as I mentioned, and now they are integrated into the CPU together. Okay, so now DRAM and GPU, they will be even closer to the CPU. Okay. Okay, coming back to the interrupt part. Okay, interrupt part, how to trigger and request the kernel service. So when do CPUs run kernel? Okay, CPU run kernel only when some special events are triggered. Otherwise, it runs user program or stays idle. So here comes the interrupt, because there are different kind of special events. First one will be hardware interrupts. So hardware interrupts including the timer interrupt or IO interrupt. So timer interrupt, which means in the CPU, there is a physical timer, and the timer will interrupt the CPU when it ticks to a threshold. So this is the reason why when you are running your program, the process will be interrupted if it occupies the CPU for a relatively long time. So the time is controlled by this CPU timer, and the timer will interrupt the CPU itself. So there is another example is IO interrupt. So when you type something on the keyboard, or when you click on the mouse, those kind of signal will interrupt the CPU. Okay, this is called the IO interrupt. Okay, so special events, not only those hardware interrupts, actually you are also familiar with the software generated interrupts part. The software generated interrupt including the system code. So such as when you are writing a program, you know you are going to read a file, to write a file, you will put a system code there. Or there are some errors, including the patch fails. So when CPU is running the program and it finds like actually the data is not in the memory, it's in some place else the memory. So CPU will find out, hey, this is an error. Okay. So this is also another like software generated interrupts. And both scenario, you can think about they are called exceptional, like special events. So someone will also call them exceptions, something like that, just like they are not the normal user program. So there are special events, then the operating system will take over the running. Okay. So I think maybe this is not easy to understand. So I have linked back to our prior example. So the same things, different process have different submarine look. So assuming process A submarine look like this. So when process A is running as usual, which means process A is running in the user mode. So the submarine will move through the surface, above the surface. So this is called the user mode execution. Okay. So if one day there is a system call occurs, so which means when the CPU read out the instruction and the instruction say, hey, I'm going to read a file. So there is a F-read system call. Then your CPU will automatically switch the tag from user mode to kernel mode. Okay, and your CPU will be redirected to ask to run the system call handler. But because this is still the same process, we don't really run process context switch. We only switch the CPU mode. So actually, the outlook for a submarine is a SAM submarine. Okay, it's a SAM user process. You can think about it like this. So after serving the system call, your CPU will automatically switch back to the stop point of the user process. The program counter will be redirected back to the stop point of the user process. And then your user process will keep running the user program. Okay. And then if your user process running too long of time, so which means your CPU, sorry, the timer inside the CPU will interrupt the CPU to say, hey, you run for too long. You need to send your CPU resource to share your CPU resource to other process. So at this point, CPU will once again be automatically stopped, and then the program counter will be switched to some other kernel, for example, the CPU scheduler. And then the CPU scheduler will say, hey, actually, which process you are going to switch to, like this. So after doing the CPU scheduler, because we are going to switch a process, so the user process, they are switching. So you can look at this example, the submarine is changed to another submarine, which means the user process are switched. Now you are running another user process, and then this is called the context switch. Okay, so the same things, after handling those kind of scheduler context switch stuff, the CPU will be once again automatically switch back to the user mode, and then the program counter will be set to the very beginning of the user process, or maybe not the very beginning. It just depends on when the process B stops last time. Okay, so process B will keep running. Okay, so now because we switch from process A to process B, so this is another user process, and you can see this is another submarine. So if there happens an interrupt, which means like maybe process B requests for some data from the hard disk drive, and hard disk drive finish the data. The data is in the like memory now. So there is an IO interrupt, and process B will be once again, the CPU will be automatically set to the kernel mode, and then the program counter will be set to point to the IO handler again. Okay, so now the IO handler can handle this kind of IO request. Okay, but the thing is, it is still staying on the same user process, which say process B. Okay, so this is possible spatial events that occurs, and this example cover, I think, most of the example here. Okay, so this is how to trigger request and kernel service. So we are going to ask for a more deeper question. So what does interrupt look like? So interrupt request. Different devices can be associated with different interrupts by means of the unique interrupt value. So if you are a little bit familiar with the system code, this is the same things. The idea, the concept will be very similar, because for system code, each system code, they have their own unique number. Like, for example, like system code, like the read system code or write system code, maybe it is corresponding to system code number, I'm not quite sure, maybe 300 something else, and maybe 400 something else. I mean, this will be a static and the operating system known. Okay. And the interrupt is doing very, very similar design. So there is a thing called interrupt request. So this is a specific interrupt associated with a specific device. And for example, for the timer interrupt, we are using the IRQ0. Keyboard interrupt, we're using the IRQ1. And usually, if you are using an Intel CPU, no matter which PC you are now using, their interrupt request will be very similar. You can just check the spec. And usually IRQ0, they are reserved, sorry, that is reserved for timer interrupt. IRQ1 is reserved for keyboard interrupt. Then there are some dynamic allocation for IRQ number for PCI device, and also there is a very special interrupt code, system call interrupt like this. Okay. So this one is about the mapping between like from a processor interrupt vector table and a BIOS and operating system. So for different layers, they have their own interrupt maintenance, and they can be remapped to each other. So this figure is just captured from the x86 architecture. So if you are using others, RISC-V or even some others one, actually this interrupt request numbers will change. For example, maybe their IRQ0 is not for a timer, it's for some others. So this depends, okay? But how does it work? I mean, physically, how does it work? Okay, so first of all, when you insert the hardware device, especially the peripheral device, into the systems, right, then they will first do the registration. So it is possible CPU will know the keyboard is mapped to maybe IRQ1, for example, and a timer is IRQ0, like this. So it just depends on which hardware wire it is connected to. Okay. So hardware device send out an interrupt signal. For example, when you click something, when you type something on the keyboard, and the keyboard will send the electronic signal to the interrupt controller via this wire. So interrupt controller, actually there's a lot of wire, and which wire receive the signal, then we can know which interrupt it is. For example, if the wire is from the keyboard, then it is say IRQ1, like this. So once the interrupt controller receives the electronic signal, it will stop the CPU. Okay. And actually, the interrupt controller will be translated to the interrupt vector like number. So in this case, there is a like table stuff here, and then the interrupt controller can do the translation. Like IRQ1 can be changed to the interrupt vector number. If you're interested in this part, you can just go back to this slides, and here is just a mapping. Like this is the interrupt vector table, and this is the interrupt vector number. So they are all mapped. They can be translated to each other. Okay. Okay. So so after the translation, the interrupt vector number will be sent to the CPU, to the local APIC part. Okay. So with this, for example, 0x81. 0x81, what does it mean? Okay, so 0x81 means it points to the 81's interrupt service routine vector. Because keyboard, when we type something on keyboard, actually the kernel is going to find where is the keyboard handler, right? The CPU needs to know what to interact with the keyboard. Maybe keyboard, like we touch like Q on the keyboard, which means CPU needs to read all the data from the keyboard buffer and then to do some reactions with it. So in this case, CPU needs to run the keyboard handler. But where is the keyboard handler? Keyboard handler should be somewhere on the memory, because keyboard handler is just like the part of the operating system kernel, right? It's just like a device driver, okay? So how to find it? So this interrupt service routine vector is going to act like an entry point for finding out where is the beginning of the code for each interrupt vector handler. Okay, so in this case, actually, the hardware part will be each vector is in a 4-byte, and then the first 2 bytes will be the code segment, and then the last 2 bytes will be the instruction pointer. So this code segment and instruction pointer, they work together. They can point to you can think about it just work like the program counter. They can point to the very beginning for the instructions for each interrupt handler. Okay, so as this H is 4 byte, so for the CPU perspective, 0x81, the number 81 vector. So which means this vector is stored on 0x324, this physical address. And CPU will read out this physical address. So inside the physical address, it stores the code segment and instruction pointer. So with using this together, we can find the first line of the interrupt service routine, or the keyboard handler. Like interrupt service routine actually is about how to handle the keyboard signal. Okay. So with this code segment instruction pointer, CPU will read out the interrupt service routine 81 because this is corresponding to the keyboard actions. Okay. So CPU runs the interrupt service routine to handle the interrupts. Okay. Oh, sorry. So this is about how CPU handle the interrupts. Okay. Any questions for this part? Okay. If this is okay, then let's keep moving. Okay. So after giving I would say like a rough introduction about kernel and then interrupt, those kind of stuff, let's get started from the very beginning. Before this lecture, we talk about device. But how to control the device from the operating system level, we need the device driver. And the flash translation layer is the firmware inside the device. So it's not about the device driver. Okay. So this is a split view of the kernel I/O stacks. This is our applications. And here are a lot of different hardware devices. There are keyboard, mouse, SAS, USB, PCI bus, blah, blah, blah. And then for each keyboard, mouse, or even different device, you can think about there are microcontroller on each device. So to communicate between your CPU and the microcontroller, you need some way. And the device controller is the way for the user to, for the CPU, the whole CPU to communicate with the controller. And device controller is also like, for most of the design house, like MediaTek, Realtek, usually their engineer from a computer science, they are doing this kind of device controller development. Okay, so I think this part is widely used in Taiwan's industry. Okay, like this. Kernel I/O systems, and at the very bottom for the kernel, there is device driver. So this is controller, and this is driver. Controller is just like a tiny CPU. So different device, they have their own controller, and there is a device driver to talk to them. Okay, and for each device controller, you can think about what it runs on device controller is firmware. So different different device, they have their own firmware, which means different controller will run different things. Okay. So there are the definition for something else. So there are two different kind of device. One is called block device. The other is called character device. So block device is an addressable in device specific chunks called block and generates POSIX, just like the random access of data. So block device, you can think about just like hard disks, like SSD. They are continuous, a really huge like space. You can stick to any place to read out the data. Okay, so this is called block device. And usually like file system, and then it is suited for handling data blocks with a fixed number of bytes, something like that. Okay, and there is another device called character device. So character device is usually to handle like streaming data. So like keyboard or like your screen, usually they're handling the streaming data. So as they are streaming data, so which means you cannot use SIG because the data is not already there. I mean, the streaming data means the data comes in a runtime. So you cannot use like SIG or to read out data. Okay, so this is about the character device. So here are like keyboard, mouse, or PCI bus. They are all for character device, and like USB device and SAS plug device, they are called the plug device. Okay. So let's talk a little bit more about the device driver. So device driver, you can think about 70% more about of a Linux kernel code is device driver. And this is like the Linux like 2.6 breakdown for different device driver. So among them, there are 50% they are for character device drivers, 16% for block device, 27% for network device drivers. Okay, so different device they need their own device driver. So this is the reason they have a super large code base. Okay. So here comes an example of the like network device driver. So this device is going to connect your, for example, your notebook with the Ethernet, because in a prior time, like there are some notebooks, they cannot directly plug in the Ethernet, or even for some like very slim notebook, they don't want to keep the Ethernet socket. So you need to use this kind of adapter to link your computer with the Ethernet. Okay, so for this one, they'll connect the USB with the Ethernet part. So the I/O stack will look like this kind of stuff, because this is for the networking. So probably like there is a Linux network stack will be involved. So there is a TCP/IP stack, and then your package will first encapsulate according to the TCP/IP protocol. And because we are going to send this kind of package via the USB. So USB to Ethernet driver is needed. So in this case, if we are going to send data from your notebook to the internet, then you will be encapsulated with the USB. Okay, with the USB like package. And then USB bus driver will to make sure those package format. Okay, and then USB bus, then USB to Ethernet controller device. Okay, so you can think about like even this tiny device, there are at least three driver inside. There is a control between the USB and the internet. There is an Ethernet controller. There is a USB controller here. So different controller, they will have their like device driver to interact with. So this is about like very briefly idea of about a device driver. Okay, so this is about how to build a device driver. So usually device driver is a computer program that operates or controls a particular type of device that is attached to a computer. And usually the device driver that looks very similar from each of the other, because they are defined in a very typical way. So you can see that like for every device driver, there existing module init. Module init just like a constructor. So when you are writing a C++, you need a constructor. And when you are writing a device driver, you always need a module init. And when you are going to terminate the device driver, the last step for the device driver, it will run the module exit. So in the C++, it's just like your object is going to be destroyed, then you will run a destructor. So they are very similar idea here. And the module init, like for the function part, like this is the function it runs. So usually it is for the initialization, but in this example, it's just going to show you it used the print k, the kernel print function to show, hey, there's a hello world. And then module exit function usually is going to deallocate the resource allocated for this device driver. And this example is just going to show you like a goodbye signal. Okay, so I think we can call it a day, and next week we'll resume from this part. Thank you, guys.
这个条件性好像就是可以，就是我之前那个版本是参加那个比赛，
对，
的阶段，但是因为我后来。